I say, don't hesitate to interrupt. We ended yesterday on a somewhat passionate, emotional note, and I thought I should start by addressing that issue. And it comes down to, I think it's Steven Weinberg, who's a physicist at Texas now, who observed that scientists are as interested in the history and philosophy of science as birds are in ornithology. And so a bird doesn't care in the least what the people who observe the birds and study the birds think. They do their thing. And many scientists, there are some universities have departments called the History and Philosophy of Science. Princeton has one, and they had a conference once on oceanography, history, and I consider myself an oceanographer. To my amazement, I was the only oceanographer in the room. So there are people who study us as if we were birds, and they have, and the most cited book in this field, History and Philosophy of Science, is a book called Small Science into Big Science. And what's most amazing is that most scientists don't know of this book. I recommend it very highly. It was written in the 60s, and basically you can treat science, there's a topic called the science of science. You take all the papers that have been written, you look where they've been published, who references who, and you ask yourself, what can I say about this activity called science? And it's fascinating. Maybe at the end of the day we can go into that issue. But what amazes me most is that scientists are unaware of this field. If you want to know, so if you don't want to learn about the history of philosophy of science, what should you know about it? And I feel there are two big things. The one I've put down here is we're in a catch-22. We make observations, and then we develop theories to explain the observations. And people as prominent as Newton thought that these were separate activities, that you can make observations, you collect all the facts, and then once you have the facts, you step aside, you explain them. And Charles Darwin knew that's not possible, that to make an observation, you need a theory, you need a model. And however, you also need the observations to test the model. So it's a catch-22. How can you make observations? How can you have a model to interpret observations and then use the observations to verify the model? The model could be wrong. And there is no escape from this, and we'll come back to this repeatedly, that in science, so there's a science, we never know the final answer, right? Science, there's always the possibility that there could be a different answer. So everything we say is tentative, which drives politicians crazy. And however, we scientists, and our job then is to question. We have to question constantly. The second area, so I'll try to emphasize this sort of repeatedly today. The second thing to note is that science has severe limitations. And that was the essence of the discussion at the end of yesterday. Science explains how things work. Science does not tell you how to live your life. Okay, and so you could say the debate between Graciela and Michael yesterday was Graciela had advice for us on how we should live our life, what our big concerns should be. Michael insists that that's not the business of science. He is quite correct. However, she is correct in that we as scientists wear two hats. We are scientists and we are also human beings. And we have beliefs that we think that some things are right and some things are wrong. And so the challenge to us is, how do you bridge this? We have to accept she's right in that we have to act on our beliefs in certain respects. He is right that science, this institute, cannot tell us what we should do. This is a mathematical institute. It can prove theorems and so on. It doesn't tell us how we should live our life. And I must confess, I had a talk prepared. And after the discussion yesterday, I decided I should change it. So this talk may not be very coherent. I haven't had enough time to put together. But I feel there are certain issues that merit a discussion and that I should bring to your attention. And so I've sort of digressed. So the first thing I want to start is, in any science you need observations. You cannot do without it, because we have to test our theories. And if you look where's been the most progress in, say, the earth sciences, it's simply those branches where observations are abundant. And in oceanography, the problem of surface waves, if you look at the surface of the ocean, it's waves up and down, very turbulent. That problem has basically been solved for the simple reason that to get measurements, you just need a few days. A few storms go by. In our biggest achievement in the year we're going to get into a bait on the bus here, Michael pointed out that the prediction for Guanajuato this week was for rain. And he says just shows how bad weather prediction is. I'm of the opinion that one of our biggest achievements so far is weather prediction. And, and for the simple reason that they get a test every day. Weather changes very fast. And we can come back, but I would argue in our business, we don't deal with repeatable phenomena. It's not astronomy where a planet goes around the sun and that's it. Our phenomena don't repeat themselves, so there is no alternative to many realizations. And the weather people get a different one every day. If you ask why did studies of El Nino improve remarkably, say from 1970 to today, is it has a time scale of 3 years. And after 20, 30 years, you've seen 10 realizations. So it was simply seeing more phenomena. We cannot do without measurements. So the reason for this explanation, for this digression, is to explain why I, who know basically nothing about paleoclimate, will now proceed to give a lecture about paleoclimate. And the reason is that by my field, both oceanography and climate in general is in serious trouble for lack of measurements. And that we have no choice but to pay attention to paleoclimates. In the case of oceanography, the ocean circulation, there are books on the topic, and some of you may have read these books. There's a well-known one by Gill, one by Petlowski. The other Gill, Adrian Gill, Petlowski, recently Jeff Wallace. They're full of equations, and I've no doubt the equations are solved correctly. The question is, do these equations and their solutions have anything to do with the oceans? And we're actually not sure. There are furious debates about a thing called the thermohaline circulation. And I would submit that it's a matter of belief, that the time scale for that circulation is 100 years. There's nothing that you can go and measure over the next 5, 10 years that will shed much light on that. This is sort of an embarrassing topic. So you have oceanographic institutions. We have one in Ensenada, San Diego, Woodsole, and so on. What are these people doing? They're studying the ocean circulation. The beneficiaries of what they're doing is going to be our great-grandchildren. Then we'll have enough data, maybe. So how do you test if the stuff in Petlowski's book is right or wrong? As I said, mathematically, it's fine. You write down equations, you solve them correctly. Do they have anything to do with the ocean? You're obliged to go to paleo records. In climate, similarly, in spite of what Bala was saying yesterday, I don't think climate has changed significantly over the past 1,000 years. So I would submit we have models now that reproduce the climate of today with fair realism. Is there any reason to trust those models for other climates? I will say no. The big debate, if I want to summarize the debate about global warming in one word, the word would be clouds. We don't know what to do about clouds. So the clouds are problematic because they cool the planet, reflecting sunlight. Albedo is 1/3 for this planet, and half of that is due to clouds. And on the other hand, the most powerful greenhouse gas is water vapor. And so they also heat the planet. For the climate of today, the cooling winds, our planet is being cooled by the clouds. In a different climate, what kind of clouds will we have? What will they do? It's a bit, the forecasts for global warming, for the simple reason you can't trust. Okay, and this puts us in a dilemma. So when we get the big climate issue, obviously, is global warming. Now, and it's become very polarizing. But let us for a moment set aside disagreements, and let's assume there is agreement that we are in trouble, the rise in CO2 is a problem. Then the next thing we want to know is what should we expect? And we're obliged to go to models. Now, I've just said we can't trust the models. The problem is worse because most people have not the foggiest idea what a model is. So how do you persuade them, how laymen? So we're very disconcerted. People will constantly say the scientists, the vast majority of them agree global warming is a problem. Nonetheless, if you take polls, people are completely divided. Okay, so there's a serious communication problem, and I'll get back to that on Friday. Why do we fail so badly in communicating science to the public? So I want to show you if I had to persuade somebody that, let me just finish this business. So I get involved in paleoclimates, and it's yet another example of cultural strife. In mathematics, in science in general, we have many disciplines, and we tend to put them in a hierarchy. So a place such as this, devoted to mathematics, is at the top. It's mathematics, then comes physics, chemistry, and so on. Down here is geology and psychology and so on. Now, Stephen Jay Gould wrote about this topic, and he pointed out a big difference that if you ask somebody what's the most interesting scientific question, then the answer is how did we, Homo sapiens, how did we humans get to be here? And the answer to that question is a story. You can start wherever you like with the dinosaurs, and they create a little niche for mammals and so on, and here we are. And the story is a succession of accidents. A meteor wipes out the dinosaurs and so on. And it's a major challenge to reconstruct the story. And so this is a far, far more difficult problem. So you can say in this hierarchy at the top, we started with, we put at the top the field that deals with very simple problems. And a simple problem is one that has a completely objective answer that everybody can agree on, independent of your race, color, creed, whatever. Mathematics, 2 + 2 is 4, is no debate. As you go down this thing, matters become much more subjective, because to prove how we got to be here, we got to be here entirely in accord with the laws of physics that govern everything in the universe. But it does us no good if we want to explain how humans got to be here. You have to tell the story. And it turns out the two cultures, what I will call the reductionist culture, people who start with equations, and the people who take the historical record and try to reconstruct the story, we approach the questions we try to answer in entirely different ways. And at MIT, many universities will have paleontologists, people who study the past and tell us how we got here, and they will have mathematicians. So, and sometimes they're even in the same department. And if you go to the Woods Oceanographic Institution, the paleontologist is in the basement of some building, and the Pedlowski's on the top floor, and I don't think they even know each other. At MIT, there's a similar thing. There are paleo people, and they try to get together for the reason I just said, that they need to talk to each other. And the first meeting, I think, lasted 10 minutes. People walked out. If you thought you saw some passion yesterday, it's nothing in comparison with what can happen. So the paleo people proudly will say we are storytellers. But now this has become a kind of insult. If you want to insult somebody, you say you're just a storyteller. You can't prove anything. So there is a huge cultural divide between the two groups. And when I finally get to the topic I want to talk about, I have to alert you, I entered this problem because the only test for the things I was working on was paleo. And I looked into it, and I was absolutely bewildered. I believe they think they have explanation for ice ages. I'm going to talk about ice ages. And I was not at all convinced. And every professor thinks that what he works on can solve every other problem. And so I work on El Nino, and I decided that the ice was actually incidental to ice ages, that the whole thing had to do with the tropical Pacific, because that's something I know something about, and so I was convinced this must explain everything. And so I made the mistake of giving talks with the title, Is Ice Incidental to Ice Ages? And I didn't realize if you spent, going to Antarctica may sound romantic, but it's quite a miserable place to go to. And if you spend much of your life there, you don't want to be told that you've gone to the wrong place, that there are other places you can study better. And so I finally wrote some paper, and much of my work is in collaboration with Marcelo Barrero, some other people. And the papers we wrote sent it to colleagues, and the response have been one of two things. Either complete incomprehension, they couldn't understand what we're talking about, or extreme annoyance. People are actually quite angry. And so I spoke to the paleo people, and they convinced me I have to pay attention to what they have done and point out in some very specific manner where I think they've gone wrong. I can't just ignore and say this is nonsense and here's a different idea. Why should they pay attention to a different idea? So I'm still struggling with that, and I'd appreciate your response. So this is the umpteenth time I've given this talk. I hope the response is going to be neither incomprehension or irritation. I need some suggestions as to how to get the message across. So let me go back. We start with the interest in global warming. And if you ask me, how will I persuade a layman that we face a problem, I would show him this curve. And suppose for a moment, don't look at the axes. The bottom is time, the other is temperature. Suppose that this was the vital sign of a patient in a hospital, right? Sometimes in hospitals you'll see a little chart how the patient is doing. Then in this case...
Is that actually supposed to be mean global temperature, or what exactly is it?
Well, it's temperature in polar regions. And one thing I should point out, how these people know what they know is quite a challenge. I for one, don't know how they know what they know. But anyway, so suppose this for a moment, this was the temperature of a patient in the hospital. The patient starts out with a high fever. The doctors do something right, the fever goes down. And then the patient starts having these convulsions. And they're getting bigger and bigger, and it looks quite serious. And then you blow up in the top right, and you notice that very recently there is there some pointer? Very recent.
The front.
Anyway, very recently, look at the top picture. You see this red spike.
Don't worry.
You see that red spike. And what's interesting about this picture, and so, as I said, this is the vital signs, something is going seriously wrong with this patient, and you'll probably rush him to the emergency room. Okay, so the patient, this is actually not a patient, this is the temperature of our planet, and it's the temperature in polar regions. So every schoolboy is expert on dinosaurs, knows it was very hot and humid. It was so hot and humid on the planet that there was no ice anywhere. You can find crocodile poles in Arctic regions. You can find traces of palm trees. So it was a completely different world. We then cooled, and the amazing thing is everybody knows about that, and nobody knows about this amazing journey our planet went through subsequently before we got to today. These are the current ice ages, and I've blown up the time scale there. So the immediate response of a statistician or physicist will be that this is just an artifact of more high resolution and more accurate measurements. It turns out not. You can blow up other little bits here, and never mind how they do this, but you don't see anything like this previously. So we live in a most unusual era. We live in the era of these are ice age fluctuations. And what I find astonishing is how relatively simple that picture looks. This they get from drilling into the sea floor, where the bugs that live in the ocean surface, when they die, they sink, and so you have a record on the sea floor. This they get drilling into Antarctic ice cores, drilling into the ice, and they've now extended back 700,000 years. And if you take away that little thing there, and you had to make a prediction, it's quite obvious an ice age is imminent. Right? Any 1,000 years now, there's going to be some glaciation. However, this is CO2, the red, this is temperature. Over there, see that little bit? So most of this is ice age, and then there are interglacials. The interglacials is what we're experiencing now. Everything that we've accomplished, starting with the invention of agriculture, building cities, everything we did in that little bit of time. So we took advantage of a moment. So we arrive around here. We go through all these upheavals. We amount in not very much, meaning we Homo sapiens, until this little bit. And we develop so rapidly that we ourselves become geologic agents capable of changing the planet. And this is what we're doing. And that was sort of the point in Graciela's pictures yesterday. We're very recent arrivals. We've developed so fast that we're perturbing the global system. And as I said, what do you want to do next? And that's the big problem. We need to know what's going to happen, but it turns out the models we have, I submit, we cannot trust. So there are major international efforts. I'm not sure I had time to put a picture. So there are major international efforts. What will happen next as CO2 levels rise? As the climate models, clouds is the big problem. And so there's something called PMIP. It's a huge one of these IPCC organized things of which I've become very skeptical. There are, I don't know, maybe a dozen institutes around the globe with huge climate models. You require a supercomputer. And all these people are asked to simulate the last glacial maximum, to test the models. And the last glacial maximum would be this period right there. Can you simulate that stage? Now, there is two major problems with this. The uncertainty in the data is enormous. Okay. So, first, there's a great paucity. There's actually not much data available, very little. Secondly, the uncertainties are usual. It's the kind of thing that we heard about from Bala yesterday. The uncertainties are so large that if you ask what were conditions in the tropics at the time of the last glaciation, there is in the literature debates as to whether conditions 20,000 years ago corresponded to El Nino or La Nina. Now, El Nino and La Nina are opposite states. If they're having a debate about which of these was relevant to the last glacial maximum, they really cannot know much. So there's a serious. So I would claim this PMIP thing, I hate to be crude, but it's a pointless exercise. I don't see it going anywhere. I don't see how it can lead to, we just don't have enough data. Okay, so if you deal with serious problems with your data, the way to improve matters is to filter out some of that uncertainty. And so there's a recent paper, I think Science or some big name journal, Clark plus 30 authors. So this is a major effort. These are major names in paleoclimate. And they, instead of focusing on that period, study the deglaciation. Okay, so the deglaciation, they ask, you see this repeated things, what on earth happened there, what happened there? You have these periods where very suddenly the ice starts melting. And they focus on the last one. So the key thing is what they do, instead of focusing on one point where you have huge data uncertainty, they go to a period. And then they do a very clever thing. They reduce the data to 2 EOFs. So that is the empirical orthogonal function. Okay.
The leading eigenvectors of the covariance that Bala was talking about.
Okay. So from my perspective, it's a clever way to get rid of the uncertainty, or to reduce the uncertainties. Okay. It's a kind of filtering. And this is one that the people in weather forecasting have used very effectively. If you want to, how do you know that the weather forecast for tomorrow is good or bad? It's a very complicated pattern. Eugenia showed us a picture. She showed us only one picture at 500 millibars geopotential height. There's winds, there's temperatures, all sorts of things. How do you test that your forecast is good or bad? How do you score it? And what they do is to project a forecast for the next few days onto a few EOFs. Then they take the observations and identify the few EOFs. Then they take the model, make the forecast, project the results onto the same EOFs, and now you can compare, and you have some score. Okay, so if you go to big the European Centre, for example, it shows how the models have improved, and they're sort of asymptotic now. Say the 4 or 5 day forecast, it's extremely good. What they do is...
If I may just remark that the leading EOFs have very little spatial structure. They are very large scale. Mm-hmm. So the results on large scales are very good. we don't live on very large scale.
Yeah. No, never mind. We'll come to living later. Anyway, so this is a very objective way to score your performance in a very complicated phenomenon. And as I said, what these people are trying to do here is the same for much, much longer time scales, 10,000 years. So weather forecasting benefits from weather changing daily. And you can check your theories. So they rerun the model repeatedly. They change the cloud. They change all sorts of things in the model. They tune the model until they can get a good score. Okay, and this has now taken, I don't know, 10, 20 years. And now we have models tuned extremely well. Clouds is a big part of the story, and the models can now tell us what's going to happen over the next few days. So in principle, you can do the same here. The problem is we cannot, yesterday Machoso gave a talk, we cannot run many, many cases for 10,000 years. So computer limitation, limited computer resources is a problem here. Okay, so if you go, okay, I think I'm going to run out of time. I'll go quick. What I'm going to offer is a strategy for dealing with this. So the problem we face with paleoclimate studies is data with lots of uncertainties, not very much in quantity, not many points where we have data, all sorts of problems with the observations. On the other hand, we have models, and the models have their problems. So I'm going to argue that the solution to this is to have a constant interplay between models and a hierarchy of models, not a single model. So let me just give you briefly, I want to impress on you, as I said, relations between the reductionists, the people who start with mathematics, and the people who describe what actually happened, is not a good one. So I want to impress on you how impressive has been the accomplishment of the paleontologists. So you could take them outside and they would look around and tell you that there were glaciers. How do they know? And this started in the 1800s. And it comes from looking at scratches on the rocks, from looking at the location of rocks. If you ever get to, say, Cape Cod, the Oceanographic Institute, if you look around, you'll see huge granite boulders. The place is actually a big sand dune. So how did these granite boulders get there? They came from thousands of kilometers north in glaciers that flowed. So it's impressive to me that these people could reconstruct that there had been glaciers. They could even reconstruct that there had been a succession of glaciers over time. And so what you see today is just a snapshot of a constantly changing picture on these very long time scales. And then a fellow called, to give you some idea of how amazing this was, this is a picture, there's North America, we sitting over here somewhere. So the North Pole is at the center. And then if you go across, there's Greenland, there's England, there's the Alps, that St. Petersburg, that's Moscow. Over here is Peking, Calcutta. You get some picture. Anyway, look at the blue line. Okay, that was how big the glacier was over the northern hemisphere 20,000 years ago. So it was a radically different climate. This went several kilometers high. Okay. The ocean surface fell by 150, 60 meters. Right, how high is this as well before? An enormous amount of water was transferred from the ocean onto the continents. So this was a major, major climate change. And you can ask, what?
How do you explain the yellow parts in Alaska and in what parts?
There were no glaciers here.
No,
Oh.
I mean the northern part.
Oh, yeah.
Those yellow things?
Yeah, this is what we have to explain. These are just the observational facts. Okay, so the puzzle is explain this now. Why was it so different 20,000 years ago? And if you want...
His question is, how come that you have bare ground rather than 3 or 4 kilometers of ice in places that lie north of,
this?
No, my question is,
No.
yeah, exactly.
Yeah.
At that time, at that moment, how come you didn't have ice
There,
In
there?
Alaska.
in Alaska.
North Alaska?
Yeah, good question. We're going to have many more questions that we can't
or
answer.
in Northern Europe.
So there's a possibility, should we believe this? Is the measurement, that's one possibility, the measurements are incorrect. or if it is correct, we have a major puzzle. Okay, we'll come back to that. Another thing is, so North America was absolutely covered with ice. You don't see Great Lakes. That's Washington, D.C. I live just north of me is where the glacier stopped. If you go to New York City, you go to Central Park. It's quite amazing. In Central Park, you get pictures just like that. Anyway, what I want to impress on you, it was a major achievement of these people to document this, to document that it happened repeatedly. And then the hero of the story is a man called Milankovitch, who proposed that the glaciers were responding to local changes in sunlight. So we all know about day and night, right? So
Sorry, it was Köppen and Wegener who proposed the idea, as Philander who carried out some computations.
Awesome.
I have a little bit of reservation with respect to that.
Okay, anyway, we'll go into the history. But my point is this community, at a very early stage, were on the right track. And they became aware that we know of these cycles, but there are additional cycles. This one is related to the eccentricity of the Earth's orbit. I'll have more to say about it. This one is related to the tilt of the Earth's axis going back and forth. This one is the eccentricity of the Earth's orbit itself changes sometimes. You get all this information strictly from astronomy. You take Newton's laws, you look at how the other planets, so it's mostly the big planets, Jupiter, what's the other big, Saturn, whatever, how they affect the Earth's orbit, and you can come up with these calculations. And they've now been refined, so there's a whole branch of celestial mechanics, people calculating these things. And this is just an example. If you sit at one place, this is how sunlight would change over thousands of years. Okay.
At a certain location.
At a certain yeah. So Milankovitch proposed that, suppose sunlight, the glaciers extend to 60 north, that the sunlight will increase, decrease, and the glaciers will respond. Now, then during World War II, isotopes get discovered, and they have and now they drill into the seafloor, and they come up with records such as this. So up to this time, it's quite amazing. The information was strictly from continents, and it was strictly about glaciers. Now they discovered this enormous thing, and it seems to confirm Milankovitch in that you can do a spectral analysis of this, and the periods you get out of, you'll get spectral peaks, and the periods are these periods. So this seems to confirm, so the challenge now is we know a forcing function very precisely. How does it induce a response? But the picture quickly gets more complicated because it's not just glaciers. It turns out this is sea surface temperature at various places. So this is a map of sea surface temperature up there. And just a quick digression. Earlier I told you that the present is a very unusual moment in the history of the planet, right? Going back to this picture. So we're sitting right there. Anyway, you know what I'm pointing out. We're sitting, so we're at the interglacial. They don't come along often. So my question to you is an unusual moment, present. If you look around, if you step outside and look globally, what will tell you that this is an unusual moment in the history of the planet? Is there anything you would see outside that strikes you as most peculiar? Outside meaning global, not locally here in central Mexico. And I submit that the most unusual thing you could see outside is cold water at the equator. If you ask the ancient Greeks what to expect at the equator, they would never. Most observant, intelligent people will not guess that if you go swimming in the Galapagos Island, you need a bodysuit. And what this graph tells you when they drill into the seafloor is that it's actually a recent phenomenon. It's about 3 million years ago. And these different dots and so on are just different proxies for the same thing. So they don't actually measure temperature. I've plotted temperature here, but they haven't measured temperature. They've measured something else. And there are various other things, and we need an expert on that. As I said, I don't quite know how they know what they know. But they know that if, and then they go to others, these upwelling regions, we'll get oceanography tomorrow. But if you go to Swakopmund, there's a place in the tropics, extremely bright sunlight. It's frigid if you go to the ocean. It's so frigid, there's dense fog clouds over that. If you had gone to Swakopmund 3 million years ago, it was quite a pleasant place. Okay, so something I said the last 3 million years has been unusual in the history of the planet. And it shows up in various parts of the globe. Okay, and so in particular, another peculiar thing is, the story now gets complicated because if you look at the Western Pacific, it did not change. The Western Pacific stays warm. So the picture is getting more complicated quite rapidly. So instead of just glaciers, so you can't claim that the glaciers changed the albedo of the planet and this changed the temperature everywhere, because the Western Pacific somehow isn't aware of this. Okay, so it must be more complicated than just glaciers.
Is there a snapshot at the same time of the glaciers of the South Hemisphere?
Yeah.
Is it was also
Okay, so the Southern Hemisphere.
very cold or unusually cold?
Yeah, so the picture I had earlier, I should say something about. Lots of results come from the seafloor. You drill various places, and I just showed you a picture for the Western Pacific, Eastern Swakopmund. Then a big source of information is Antarctica. And Antarctica is a huge ice core. And so here you get from this, so this record comes from the seafloor in various places, and you can average and come up with, reduce uncertainties and so on. That variable there is a completely different one from Antarctica, and you can see there's a high correlation between if I were to blow up this one and that one. Okay, so we see the same signal all over the place, the same signals, but there are some differences between them. Did I answer your question? I'm going to, one of my points is going to be that this problem has grown more and more complicated. So it starts out with Milankovitch thinking it's glaciers. And in fact, history is a big part of our problem. And then Milankovitch seems to be so successful once you get the long time series because you get the same frequencies. Many papers still will show you sunlight at 60 north in June. Milankovitch says that's what affects glaciers. And put it next to temperatures from China, from Antarctica, as if the glaciers control everything. Okay, and my main point is going to be the picture is enormously more complicated now, but I better hurry. If you want to know what happens, this is what happens during El Nino. Everybody familiar? So there is this cold water I was carrying on about. There it disappears completely. So we think that this is what the world looked like 3 million years ago and before. The top one. So we call that a permanent El Nino, and we'll come back to that. I notice Elie Zimmerman is going to give a talk. There's big debates now. So El Nino, these conditions at the top lasted for, I don't know, a few months at most, a few weeks. That was in 1998. And it caused a climate change globally. Right? California, all over the place, changes in climate. Imagine those conditions persist permanently. Then the world's climate will be completely different. So I can say we need tests for the model. So here's a test for the model. Can they reproduce a world where this is permanent? And this has become a major debate. So the big climate models are unable to reproduce such a world. So I've said they've been tuned to get the world of today right. In the world of today, this reflects the average state of affairs, the bottom picture. We've tuned it to that. If we then run these models...
No, they're not terribly good at that either.
Anyway, if we run the models and try to reproduce this world, the top world, the models drifted back to this one. Okay, so previously there was a climate drift problem with the models. They drifted to a world that was too warm. We introduced something called flux correction. We claim that we've gotten around this difficulty. We now have models that don't need flux correction. We actually have flux corrections, and they correct us to the world of today. So if you try to reproduce a different world, then you can't stay there. So there are big debates. The modelists are very defensive. They claim their models are fine, that the observations are in question. Okay, so you just questioned some observations. There's lots of things you can question, I assure you. And I will show you, just point out one stupid debate that's been going on. These are different. The blue point you see here, and the green and the blue line and the red, I'm sorry, forget about the red. The red is in the Western Pacific. But the blue point are all different measurements. The blue, green, and the continuous line, different ways of measuring the same thing. This point here, I don't know any statistics, but I would say this must be a bad data point. This one.
At the bottom.
This one there. This has actually led to big debates. Two papers appeared in Science in succession. The one, the Prince or somebody at Oxford presented these blue points, and the next week somebody from somewhere else presented the green points. And the one said the Western Pacific was very cold at that time. There was no permanent El Nino 3 million years ago, and the other one said it was warm. And this debate is still going on. Her name is Rickaby, she's at Oxford. She analyzed the data and got this point. And it gives you a feeling for how much the uncertainties are and how we need competent statisticians to sort this out. But there are debates about these issues. So, so we have, if you think it's just sea surface temperature, it's the whole climate. Sea surface temperature is highly correlated with rainfall. These are rainfall patterns. And it rains heavily where the water is warm, over there, and then it does not rain. There's no rain over here where the water is cold. So the tropical atmospheric circulation is quite simple. It's a direct thermal circulation. Air rises where it's very warm, subsides where it's cold. And so we can take measurements of temperature and sort of make inferences about what the rainfall patterns probably were. Right, so during El Nino, when that changes, Peru gets torrential rains. Everything is in accord with this high correlation between temperature and rainfall over the oceans. So today we look at this as a picture of concentration of chlorophyll. And it basically shows the climatic zones. So over the continents, you see the Sahara Desert. If you wonder why is that so red? Red is very high chlorophyll. That's Lake Victoria, completely polluted and now covered with all sorts of plants. That's the mouth of the Congo River. That's the mouth of the Amazon. The intriguing thing is you get tropical jungles, you get deserts. The intriguing thing is the oceans too have climatic zones. The oceans also have the equivalent. And so the ocean is in some sense an upside down atmosphere. The ocean doesn't lack water, obviously. What do you need for life? You need water, you need sunlight, you need some nutrients. So the surface, we'll come back to the oceans tomorrow, but the point is the oceans have climatic zones, the same that are the counterpoints of the atmospheric climatic zones. And then I will argue the sea surface temperatures affect the ocean, so these things can't be uncoupled. It's an immensely complicated problem, and now we're told that in time this changed radically. And then glaciers over here expanded enormously. There was something I was going to say earlier when you asked about the southern hemisphere. We pay most attention to the northern hemisphere because the southern hemisphere, Antarctica, is limited. Once it's white, it doesn't matter if you put more snow onto it, it's not going to affect climate that much. Whereas these glaciers up here can expand in area and contract. And so the albedo has a much bigger impact on the albedo of the planet. So we pay most attention to
the ocean doesn't froze.
Yeah, so that picture showed. So this is summer ice, winter. So there's a seasonal cycle. Part of the ocean gets ice covered. And even today around Antarctica, the ice extends away from Antarctica, contracts. But that's a small signal in comparison with a thousands of years one. Okay, so where am I? So then it occurred to me also yesterday, it was done with me years. This is a mathematical institute. I sort of assumed that people will know meteorology, atmosphere. I should just briefly explain. It's impressive how well we can explain many of these features by means of a hierarchy of models. Mitch also mentioned, or somebody mentioned, hierarchy of models. So your first attempt explaining what's going on here, while you have deserts in some places, and jungles in other, is to start with a water-covered globe. Take away all the continents. And on a water-covered globe, the circulation looks like that. So the equator is special for two reasons. It's the place where sunlight is most intense. So there's a big temperature gradient between the poles and the equator, and that drives atmospheric circulation. It's that temperature gradient. If the planet were not rotating, then the winds would all be strictly equatorward. It would be like Venus. Eugenia is the expert on Venus' circulation. Venus almost doesn't rotate. planet Earth rotates very fast, so the Coriolis force comes into play. And as a consequence of Coriolis force, the winds on our planet are mostly east-west instead of north-south. Okay, so in particular, you get easterly trades in the tropics. They converge onto this region of heavy rainfall. You get westerlies in mid-latitudes. You get deserts. So the air goes up here. Where the air goes up is where you get heavy rainfall. Where the air comes down is where you get deserts. Okay, so these places are all connected. And as I said, what's astonishing about this very simple model is how much it gets right. Okay, so the next thing you have to do is put in continents, and the continents have different thermal properties, and you can distort things. You can gradually build up a more and more complicated model. In the end, you have a big GCM. So let me just take a minute or two to say something about the GCM. So we, at the moment, maybe it will come up in the slides. I was going to say something about the value of simple models, but also the dangers in using simple models. But let me just show you some of the measurements we now have. So they drill all over the place, and these are the signals they get. This is for ice volume. This you get at the high northern latitudes. This is for sea surface temperature in the tropical Pacific. This is for probably rainfall and caves in China. And if you look carefully, that's just a blow up. I may come back to this. It's the same signals. I just wanted to contrast them with one another. So now we have records, and the main result that emerges from this. Let me just say, we start out, this was Milenkovich's picture, that you have sunlight shining on glaciers, and to him that was the end of the story. The glacier changes in sunlight cause the glaciers to wax and wane. Okay, then the next step was to accept that the glaciers, they change the ocean circulation, they change the atmospheric circulation, the ocean and atmosphere interact. The story gets more complicated. However, in the minds of many people, the central part of the story is still this. The sun affects the glaciers, and the glaciers drive everything. Okay, I would submit that what we've now come to is this much more complicated picture. It's enormously complicated. The sun affects everything directly. Glaciers originally was considered phenomena in isolation, and you study them looking at how they respond to sunlight. I will now claim glaciers are just part of a global suite of phenomena. Things happening all over the place. There's monsoons in India, there's upwelling of Peru. All these things change, and that the problem has become so complex. I think I have it in words. This is what we originally thought. This is the state of affairs today. And I claim, so that everybody wants to know, why do the glaciers wax and wane? And I will claim this is the wrong question to ask. So very often in science, you're told that the biggest step, the biggest progress you can make is to ask the right question. Right? You can always find people who will solve the question for you once you've posed it. But a question, in fact, embodies implicitly some hypotheses. So I want to propose the question should change from this one, because glaciers are just too complex now. They're part of a global pattern. They're just one of many things. We should instead focus on this one. What is the response to this precisely known forcing function? And the response turns out to be these three signals. And so I'm going to argue that there are actually three separate explanations for ice ages. And they're very easy to envision. If I had a planet with a circular orbit, then precession is wiped out. Precession has to do with going closer and further to the sun. So in the world of today, we're closest to the sun on 3rd of January, but 10,000 years ago, we were closest to the sun in July. So that, most people dismiss that, but distance from the sun does affect climate. To such a degree that 10,000 years ago, the Sahara, 10,000 years ago, we were closer to the sun in July. So sunlight, northern summers were much more intense than they are today. I shouldn't say much more, about 5-6%. It was so intense that the Sahara had lakes. So even today you can go into the Sahara and you can find bones of crocodiles, animals that require lots of water. And there are even evidence of people, because at some of the rocks, you'll find carvings and so forth. That was only 10,000 years ago. So you can imagine a world, suppose we made the orbit circular, then we wiped out precession, all those effects would be gone. Would we still have ice ages? You could alternatively imagine a world in which you keep the tilt fixed. So the tilt of the Earth's axis oscillates, and as it oscillates, the poles get more sunlight, the tropics get less, vice versa. And we can explore such a world. And then the one I find most interesting, suppose there was no Milankovitch forcing whatsoever. Would I have ice age cycles? And I will claim my main point is going to be that this is probably the biggest signal we have, and it's been completely overlooked. And I have to skip some pictures now. And okay, so we're going to look at the response to a forcing function. And we can get lots of guidance from looking at the seasonal cycle. So the seasonal cycle is the biggest climate change that we have, that we experience, happens regularly. And it's a fascinating phenomena. So we can get lots of guidance here because for a start, the seasonal cycle is composed of many different things. We study each on its own. We have an explanation for monsoons in India. We have an explanation for winter storms in Canada. We have an explanation for upwelling of Peru. However, collectively, they must all satisfy some energy balance, energy constraints. And at the moment, even though we know a lot about the seasonal cycle, we don't know what is the balance between local and global. Okay, so if you ask somebody, the big debates about position of what's called the ITCZ, the region of rainfall in the tropical Pacific, it moves seasonally. What's causing it to move? So one group will
maybe you can just spell it out.
Okay, it's called the Intertropical Convergence Zone. So in that picture, in this perfect world, water covered, it's on the equator. That's where it will rain heavily. In the real world, it's off the equator. In the real world, it's there. It's sort of a major puzzle. Why is it there? Why isn't it on the equator? And seasonally, it moves a little bit north and south. And if you go to the literature, there seems to be every month now a new explanation for this ITCZ thing. And it illustrates, to me, the problem between global and local. So for example, the people who say atmosphere is driven by equator to pole temperature gradients will say, put a glacier in the north, you've changed the gradient, this will affect the tropics. So they will claim the tropics, what goes on there, is a consequence of high latitudes. Then people such as myself who study the tropics claim that the tropical ocean-atmosphere interactions locally determine what's going on. There are people who claim this ocean circulation in the Atlantic, we'll get to tomorrow, affects this. I'll show you there's at least a dozen different explanations. They're probably all right. But what happens is the people who study the large atmospheric circulation who go to the circular world, I can't find the circular world I had, they have a very idealized model in which they ignore the ocean, it's just a source of moisture, and they tell you when you change the pole to equator temperature gradient, how does the circulation change? Okay, I have a different idealized model, and I look at interactions between the tropical ocean and atmosphere, and I tell you what will happen. Somebody else has a separate model. So each model is a possible world. The big question is, and everybody could be right, however, we've ignored that we're all on one globe and that we're affecting each other. So the monsoons year to year change, even though the sunlight doesn't change year to year. It must be a consequence of something else. So this is an unsolved problem, this connection between these different phenomena in different regions. And that's the one I'm driving at here. So the seasonal cycle is a fascinating unsolved problem in that we do not know this balance. So it's quite possible to satisfy a global constraint. There must be an energy balance. The Earth receives as much energy as it sends back to space. Collectively, all these phenomena must satisfy that. The only model that can deal with that is the big comprehensive climate models, but we have to be suspect of them. Okay, so it's an unsolved problem, the seasonal cycle. What I'm going to tell you in afraid will have to stop there, is we can learn from the seasonal cycle how to proceed. The first thing you do to study the seasonal cycle is you determine the climatology. And the climatology serves two purposes. It's an artifact you never observe. So I give you data from this place for the last 100 years, and you calculate what is a typical January. You have 100 Januaries, February, March, so on. And it's an extremely valuable concept. So you've done two things when you calculate this climatology, that you've filtered out uncertainties. If you lack data for some Januaries, you appeal to this one, and you know what should happen in January. Okay, so you've smoothed that. You start with a poor, spotty data set, and you end up with something quite smooth. The other thing you've done is you've simplified the scientific problem. You deal with climatology and weather has disappeared. So we have a separate, I can explain why summer is warmer than winter without appealing to weather. I could explain why summer is warmer than winter without appealing to El Nino. So I have a separate explanation for El Nino, I have a separate. So the merit, the virtue of climatology is that it gives you, it reduces your observation uncertainties, and it simplifies the problem you want to deal with. Okay, so here I should just go back to the paleo people. Their approach, I don't want to offend anybody, is almost Buddhist, in that they make measurements. It's a very labor-intensive field. They see lots of wiggles, and they become very fond of all these wiggles. And they are reluctant to filter out anything. And so they give them names, Young Bedraiers, Oscar, Danskar. I mean, you read the literature, it's quite amazing. Every wiggle has a name. And they have explanations, or they try to get explanations for all of them. And so one thing we have to persuade, as I said, I'm an impression the Buddhists think that everything is important. It's useful philosophies for some purposes, but for paleo, it would be best to filter out some stuff, ignore them. So I would claim younger dryers as incidental. Ignore that. There are people, it's incidental. It's like weather. To explain why July is warm here, I don't need to take into account that it will rain. Anyway, there's a difference between weather and climate. And the climate problem, the big difference is, right now, if I were living in New York, I could predict with complete confidence that 6 months from now it's going to be bitterly cold. I can't predict the weather 6 days from now. So there's a big difference. It's important to realize we're dealing with a spectrum of phenomena. And so my main message is this problem has become very difficult, and we need simplifying processes. That's where mathematicians can assist. The observationalists, as I said, it's labor intensive. They want to tell stories. They don't seem to distinguish between some important and some unimportant things. They just include everything. It's a field absolutely ripe for involvement of people with different skills. The main result, I'm now run out of time. There are all sorts of questions now. So we want to know what is the response to Milankovitch, a very precise question. And there are many puzzles. If you go back to that map I showed in the beginning, the graph, something happens at 3 million years ago. What is it that caused the phenomena to start amplifying, the ice ages? Something happened at 1 million years ago. There are 3 signals. One of them is a sawtooth, and it becomes suddenly. Okay. There are basically these 3 signals in the. There is an obliquity one. So you can isolate an ice age signal attributable strictly to tilt of the axis. There's ice age signal attributable to this bottom one, quite separate. And then there's the sawtooth. And let me just, can I have 3 more minutes? Where is the organizer?
Yeah.
Stop soon.
Okay. The main point I was going to make is that what's going on here depends on feedbacks. What happened 3 million years ago is glaciers. So we go back to 60 million years, extremely warm, and then it starts cooling off. The cooling off is because of phenomena related to plate tectonics. Continents are drifting. Plate tectonics. It changes the composition of the atmosphere. The continents move around, volcanoes erupt, there's something called weathering. It's a complicated thing, but accept plate tectonics gradually causes cooling. As a consequence, sooner or later, cold water appears at the equator, and glaciers appear in the northern. The moment you have glaciers and the cold water, you have feedbacks. The feedbacks for the glaciers is obvious. Once you have a glacier, it affects sunlight, it reduces temperatures, more precipitation falls as glaciers. The glaciers grow, they produce even more glaciers, and so on. There's a positive feedback. So the moment we entered 3 million years ago, the system became unstable. Feedbacks led to bigger and bigger glaciers. Superimposed on this is the obliquity oscillations. And what happens is the feedbacks operate in a separate way. For the obliquity, if next summer is slightly colder than the previous summer, then all the snow that fell during winter does not melt. So obliquity causes a gradual increase in snow, and so I said the period was 40,000 years. You can get a 40,000-year cycle. But the key thing, let me go back, suppose there was no Milankovitch forcing, then I said the system's unstable. So you get a trend, and you can see the trend quite clearly in the records. 3 million years on, it gets colder and colder. At some point, the glaciers get so big, you reach a threshold. They cover such a big area that geothermal heat from below starts warming them, melts the water, and the glaciers go unstable.
Why that happen?
What? Once they cover a very huge area, geothermal heat from the interior of the Earth destabilizes them. So then they break up. So now exactly the same feedback causes you to warm up, go in the opposite direction. And this is much shorter than that, and then in due course there's so little glaciers that the perturbation can start the process going again. Okay, so this happens to be regular. If I took away Milankovitch altogether, it would be irregular, but I would go from ice age to interglacial to ice age. The reason that this is quick and this is slow is simply that to grow a glacier, you depend on precipitation in the form of snow. It's a very gradual process. To melt a glacier is very quick by comparison. All you have to do is shine the sun more brightly and the ice melts and goes off. So in general, this is a quick process, this is slow. My main point is that you can, of the 3 signals that you see in the records, 2 are directly attributable to Milankovitch, to precession and to obliquity. The 3rd one would happen even in the absence. And all that Milankovitch does is to time. It's a tuner, it's a pacer. It determines when you accumulate a lot of ice. It's now so big it's going to disintegrate. However, if at this time you also happen to shine more sunlight on the ice because you've tilted the axis, the whole thing is favored, the disintegration. So it turns out if you look at the time series, these are times when obliquity is increasing. Okay. So there is a connection between them. So I'm going to go to the final slide. So my main message is the ice age question has become enormously difficult. It needs simplification. And it's best for us to focus on 3 signals. There are 3 separate reasons for ice ages. 2 are fairly obvious because they're due to forcing from sunlight. The 3rd one is not so obvious. It's due to the system being unstable. The feedback support trends, the trends leads to thresholds, the thresholds lead. So I've spoken mostly about glaciers. Tomorrow I'll show how the ocean, I mentioned sea level goes up and down 150, 60 meters. The ocean does not passively give up this water. There's a transfer of water from the ocean to the land to form a glacier. I will argue that the ocean is actually an active participant in this, and that you cannot explain the ice ages without taking ocean circulation into account. But we'll continue there tomorrow.